Good day, students, and we're going to move on to the section on trigonometry. And in this section, I'm going to do the same as in the previous video, where I'm going to just look at the basic fundamental skills that you should be able to do in for trigonometry. And as you can see, it's quite a bit more than the analytical geometry. And so analytical geometry is really an area where you can get a lot of extra marks because it counts the same as trig in your final exam. So if I go here, you'll see that analytical geometry in your final exam, the weighting in the final exam in grade 12 is 27%. Okay, and then for trig, it's also 27%. And yet there's a lot more that you have to be able to do. So you can really score a lot of points in grade 12. Euclidean geometry, 33%. It's a third of your paper in the final exam, paper 2. And the other one in paper 2 is statistics, which is only 13%. So all that considered, analytical geometry is where really, considering the little bit you need to know, it's really where you can score most of your marks. Trig is definitely one of those topics that students really struggle with, and I get it. It's not as straightforward and as simple, and if you don't understand the idea of a function, then you are going to struggle with trig in general. So let's just get that addressed here quickly. So function would mean that you have a expression that if you submit something in there, it gives you an output. Okay, so for some input value, it gives you an output. And the reason why trig would be functions is because you have the trigonometric functions but what you are putting in is an angle, and what you get out is a ratio. Okay, so for example, opposite over hypotenuse. And so what this means is that if I have a triangle, okay, so if I have a triangle, no idea what, then, and it's a 90-degree triangle, that's important, then theta is the angle. If I ask the sine of angle theta, what I'm asking theta, so it's almost, I used to explain it as X is coming in for an interview with F, and F asks it a question or does something with whatever comes in, and the result produced is the Y value, the input and the output. So when theta comes in for his interview with sine asks him, okay, what is the ratio of your opposite over your hypotenuse? So the hypotenuse is always the one across from the 90-degree angle, the opposite, the one opposite the angle that comes in for the interview, and the adjacent one is that. Okay, so that is what sine does. It asks him that question. Cos asks theta, okay, what is the ratio of your adjacent over your hypotenuse? And tan then asks, what is the ratio of your opposite over adjacent? Okay, and that's just the basics. Just understand that. And so it is simply asking a specific ratio. Now, if we then go to the things that we should be able to do when we work within trigonometry, at grade 10 level, this is what you should be able to do. You should be able to find trigonometric ratios from right triangles, including reciprocals, where information is directly available. So what does that mean? It just means you've got a triangle and a 90-degree triangle, and there's values given. So let's say, for example, that is 4, that is 5, and this is something, and it asks you, okay, find sine of theta, find cos of theta. In this case, you'd have to first calculate this, and you can use Pythagoras to calculate this. So it's just a simple, straightforward calculate, given a right angle triangle, calculate the ratios. Now, it says including the reciprocals. Now, the reciprocals just mean that it's those ratios where they are turned around. So, for example, the reciprocal for sine is cosec. Okay, cosec theta is the hypotenuse over the opposite. Now that's not examined. This is a grade 12 instruction that you should be able to do. The reciprocal for cosine is sec theta, which is the hypotenuse over the adjacent, and for tan, the reciprocal is cotan. Okay, is adjacent over opposite. And so that's what you should be able to do in grade 10, but it's this specific instruction is not examined in grade 12. The next ability we should be able to do is to find the side length of a right angle triangle given another side length and two sides. So that's just literally using Pythagoras. Okay, and then recall the trigonometric ratios for special angles up to 90 degrees. Okay, so that component is important. So this is level 1, and this is very important. Things that you should be able to do. If you can't do this, like there's no ways you can continue with, if you don't understand these three things, that you can continue with trig. So let's say that third one, the special angles. Okay, so special angles would be, and I teach this special angle thing that you can study off by heart. Now, as you can see, that level 1, you'll recall what I said with level 1 is that that for level 1 you need to be able to know these things off by heart. Now there's 3 special angles. Well, 4 really. Is it 5? Okay, there's angle 0, angle 30 degrees, angle 45 degrees, 60 degrees, and then 90 degrees. Okay, and these are points on the Cartesian plane. Okay, so it's the point xy. This one is the point, and so what you're going to do is you're going to number the x values. This one is going to you're going to start with 0, and then 1, and then 2, and then 3, and then 4. And then you're going to take the square root of each. So it's the square root of 0 is 0, the square root of 1 is 1, the square root of 2 is square root of 2, the square root of 3 is the square root of 3, and maybe let me move it a little bit this way. Okay, and then the square root of 4 is 2. So I'm not going to use that, I'm just going to say 2. And then the next thing I'm going to do is do the same, but I'm going to do it backwards for the y values. So this one is going to be the square root of 0, which is 0. This one is going to be the square root of 1, which is 1. This is the square root of 2, which is square root 2. And then this one is going to be square root of 3, which is square root 3. And then this one is going to be the square root of 4, which is 2. Okay, and what we're doing is each of these have this circle is a circle with a side with a radius of 2. So the radius is equal to 2. Now, what are we doing? Well, we're actually working out the special angles, and so you can try and remember the special angles using this. It just helps to know it off by heart. So don't even use this. But if you do forget it, then you need to be able to do this. And so this can help you with your special angles. So sine of theta is opposite over hypotenuse. So the hypotenuse, or you can say, is y over r. Okay, so why y over r? Because if this is my triangle, okay, there is my triangle, can you see it? Then this is my 90-degree triangle. This is my hypotenuse, the one that is opposite my my 90 degrees, and that is just the radius. For all of these points, it will be the same. And my opposite is this red line here, and that is obviously how high this triangle goes, and it goes up to this y value. So my y value is my opposite, and then my x value is down here. So that's my x value, that's my adjacent, and my y value is my opposite. So sine of theta, sine of 60, so sine of 60 degrees is therefore my y, which is square root of 3 over 2. So it's square root 3 over 2. And then you can just use that for anyone. If I take tan of 0 degrees, for example, there's 0, here's 0. And so tan of 0, tan is opposite, which is y, over adjacent, which is x. Opposite is 0, y is 0, and adjacent is 2. So it's 0 over 2 or 0. Okay. I personally just know them off by heart. It just makes sense. And one of the reasons why it's best to actually know them off by heart is that when you identify a number like the square root 3 over 2, I can immediately tell you, oh, I know that is square root of 3 over 2 is either sine of 60 degrees or it is cos of 30 degrees. You'll see cos of 30. Now, I just know them off by heart. So the reason why it's helpful to know these off by heart, not just helpful, is it's almost necessary. And that's why it's level 1. You're supposed to know them off by heart. Now you can use this to if you forget, or you can even use your calculator really if you forget. But the problem is you won't recognize, if you rely on your calculator or you rely on this little diagram, you won't remember that square root 3 over 2 is actually sine of 60. And so I can give you a good example. So let's say I had the square root 3 over 2 cos of 60 degrees plus, let's say, sine, or rather not cos 60, let's make it cos theta plus 1 over 2 sine theta, okay, is equal to something like sine of 2 theta. If I were to give you something like that, then if you don't know, this is actually a special angle, which is sine 60 degrees cos theta, and this is cos plus cos 60 degrees sine theta is equal to sine 2 theta. Okay, if you didn't know that, then you wouldn't have noticed that, okay, this can actually transform into this, and this is actually sine theta plus 60 degrees is equal to sine 2 theta. And so now you can solve the equation. So notice that it is important to know these things off by heart. It is important to know this compound formula off by heart, because then it allows you to identify the simplification process or the manipulation requirements for certain things. But okay, that is higher level. But once you know these things off by heart, it makes the higher levels possible, and that's what I'm trying to emphasize for you. So if we go back to what you should be able to do, recall the trigonometric ratios for the special angles up to 90 degrees. Then in grade 11, what should you be able to know off by heart? The simple application or recall of the fundamental identities. So simple application or recall of fundamental identities. So there are two fundamental identities. So move this up a little bit. There's two fundamental identities, and that is that sine squared theta plus cos squared theta is equal to 1. That's the one fundamental identity. And the other one is that tan theta is equal to sine theta over cos theta. So these are the two fundamental identities, and you should not just know how to use them, but you should be able to recall them without having to know them off by without having to look them up. You must know them. The next level 1 things that we need to be able to do in grade 11 is simple application of co-ratios and reduction formulas. Now this is super important, and it's probably, I think in my opinion, this is probably the most important topic in Trig. Once you understand these basics, then this is the co-ratios and the and that's the simple application of that. So straightforward application. So for example, if I have sine of 90 degrees minus theta, that is equal to cos theta. Okay, this is something I need to know this. I need to know this, and I need to be able to apply it in simple context. So for example, if I see sine 2 degrees, I should know, sine 2 is the exact same answer as cos 88 degrees. If I see cos of 36, 136. Okay, well, let me get to that one. So this is co-ratios. The same goes for cos. That cos of 90 degrees minus theta is equal to sine of theta. They're exactly the same. And then tan's co-ratio is cot. So tan of 90 degrees minus theta is cot theta. Now this one you're not really going to use. The only reason why I'm writing it down is because the reason why they are co-ratios is because they make up the other angle in the triangle. So for example, if this is angle theta, that's 90 degrees, then that angle is 90 degrees minus theta. In other words, for example, and that's like here. So if this is 2 degrees, then that is 88 degrees. Okay, because this is theta and that's 90 degrees minus theta. So what happens is if I now say, okay, well, this sine of theta is this angle, this side here, let's call this side length A, this side length B, and that side length C. So sine of theta, sine of that angle is A over C. A over C. But if I turn my triangle around and I say, okay, but this is now my observed angle, 90 degrees minus theta, then A over C is not sine anymore, it's now cos. It's now cos, but not of theta, cos of the other angle, the 90 degrees minus theta. Okay, does that make sense? Okay, so that's what co-ratios are. They cooperate, they work together. That's why they that's sine and cosine. That's cos. Tan and cotan. Okay, so that would be the co-ratios. The next one would be the reduction formulas. And reduction formulas are these. Okay, sine of 180 degrees plus minus theta. Okay, it now depends, and again, it helps that you know these things. You shouldn't need your cast diagram. You should know it off by heart. But okay, the cast diagram helps us to determine why that is so. Sine of 180 degrees plus theta. Okay, so 180 degrees plus is there. Okay, and because this is 180 degrees. Remember, there's 90 degrees, and this is 270 degrees. So sine 180 is here. So the whole point with the reduction formula is that when you use the x-axis, and you can basically, it looks like it trims away this additional angle. And so what you're trying to do is you're trying to get an acute angle. You're trying to get an angle less than 90 degrees in here. And to do that, you use your reduction formulas. So 180 degrees plus that would be in this quadrant, and so 180 degrees plus would be a place where only tan is positive. Okay, so in that case, sine would be negative. And in 180 degrees minus, that is in this area, that is where sine is actually negative. So, positive, because it's in the second quadrant. So that gives me, so just the way I'm writing in shorthand here now, so that I can just save some space and maybe write this down quicker. But sine of 180 degrees plus theta will be negative sine. Sine of 180 degrees minus theta will be positive sine, because sine is positive in that quadrant. Now that would then also, if we choose a different one, let's say cos of 180 degrees plus or minus theta. Okay, if it's plus theta, then it is here on this side, and there cos is negative. If it is minus theta, it is here in the second quadrant, and cos is still negative there. So either way, cos plus or minus 180 degrees is minus cos of theta. And here's just a good example of that. Cos of 136 degrees is the same as saying that, well, 136 is cos of 180 degrees minus 44. So what a lot of students do is they say this is cos of 180 degrees minus 136. That's not what you're doing. You're not subtracting 180 from there, or subtracting that from 180. You are rewriting this in a new way. You are saying, okay, instead of writing 136, I'm going to say, well, 136 would be this angle here, 136. So what would that angle there be? Okay, well, just subtract 136 from 88. That would give, what angle must I subtract? I must subtract the angle of 44. Now this is therefore minus cos of 44 degrees. And so that's the idea, is that you are trying to rewrite the angle in there in a way that only uses acute angles less than 180 degrees. Sorry, 90 degrees. Okay, so for tan of theta is plus or minus, tan of 180 plus or minus theta would be, okay, positive, plus would be positive, and negative would be in the second quadrant, that is negative. Okay, because tan is negative there. So this is the one, is one of these two sides. The other way where it might be is here in the fourth quadrant. Now the fourth quadrant is either 360 minus, or it's just negative. So either way, I could have maybe I have sine of negative theta is the same as saying sine of 360 degrees minus theta. It's exactly the same thing. So either way, this would be the fourth quadrant. And in the fourth quadrant, in this quadrant, cos is positive. So sine, if I just keep to the positive, acute, and simple angle, sine would be negative. Okay. And then if I take cos of negative theta, or cos of 360 degrees minus theta, that is equal to positive cos of theta. So cos of negative angles, cos remains positive. And then for tan of negative theta, or tan of 360 degrees minus theta, all of them would be negative tan theta, because tan is negative in that quadrant. These are all the reduction formula. And again, these things you should know off by heart. That's why it's level 1. Okay, so let's see what else is there in level 1 that we should know. Routine, grade 10 routine procedure. So in other words, all of these things, so here you see level 2, all of these in grade 11 is level 1 questions, which means that you should be able to do what you could do in grade 10 at level 2, you should be able to do in grade 11 when you're in grade 11, and obviously in grade 12, you should know that off by heart. So for example, solve equations of the form a trig ratio equal to a constant for angles between 0 and 90. Okay, so let's start with that. These would also be level so basically what it's saying is if I have a trig ratio, so some or other trig ratio, theta equal to a constant number for special angles between, or not even special angles, for any angles 0 to 90 degrees, then I should know exactly how to get that answer, and I shouldn't even have to think. So again, maybe just a quick example. Let's say I have sine of theta is equal to a half. I should know that that means that theta is equal to 30 degrees. Okay, or if I have something like cos of alpha is equal to 0.83, I should know, okay, that means alpha is equal to arc cos of 0.83, and I should be able to use my calculator to get this answer. Okay, so very simple calculations that you should be able to do with that. Okay, let me just save my space here for the actual theory. This is theory. This is what I should know off by heart. Okay, so I should know how to solve off by heart expressions that are of this form when I'm working between those angles. Okay. To find an angle in a right triangle given two side lengths. Okay, so given any two side lengths in a right triangle, I should be able to, so here is given a right triangle with CAB, and they ask me one of these angles. If they give me any two angles, okay, any two angles, let's say they give me C and B, I should know how to find any one of those two angles using trig. Okay, and how can I do that? Again, this is the basics. That's what trig is all about, is working in right angle triangles. So if I have these two angles and I need theta, for example, then I see, oh, it's opposite and hypotenuse. So sine of theta is equal to B over C, and then theta is equal to arc sine B over C. And so goes any others. If, let's say, they gave me C and they gave me A, no, let's make it C and B is still given, but now I want alpha. Well, then this is my observed angle, which means this is now my adjacent side, the side that makes up the angle. Okay, and this is still the hypotenuse. So alpha is equal to arc cos of adjacent over hypotenuse, B over C. Okay, and so there's two ways in which, given B and C, how I can get those two angles. And a host of other ways. I could use get A using Pythagoras, and then I can use sine for alpha, or cos for theta. But there's a host of different ways. But make sure you know how to do this. You need to actually, when you read this, you need to be able to tick that and say, I know how to do that. Next, use the diagrams to determine the numerical values of ratios or angles from 0 to 360. Let me just figure out what that means. Use diagrams to determine the numerical value of ratios for angles from 0 to 360. Okay, so what I think that means is, yeah, I think I know what that means. It means if we have a point, an angle on the Cartesian plane, and we give a angle such as a point there, for example, and you needed to calculate what is the, I think it just comes down to, I'm not exactly sure. Not exactly sure, to be honest. What is it saying here? Use diagrams to determine the numerical values of ratios for angles 0 to 360. Okay, to be honest, I'm not 100% sure. This is what I think it is saying, because this is really a standard a standard way of doing these type of questions. Is, let's say we have a point here and they give you the point PQ. Okay, and they say that point PQ, and they ask determine that's theta, determine cos of theta. So there's theta, determine cos of theta. Now typically, so this is an angle between 0 and 360 on a Cartesian plane, and now they ask you to determine the ratio of that angle, and in this case it will be oh yes, there we go. I first need to work out the hypotenuse, which is the square root, because I'm using Pythagoras, of p squared plus q squared. Okay, first work out that, and then I can now work out what is cos of this angle here, because cos is adjacent, which is x, over r, which is the value, in this case, p over the square root of p squared plus q squared. And so p and q are actual numbers, but you hopefully get the point. Is you should be able, if they give you a point on the Cartesian plane, to calculate the ratio for the angle that point makes with the zero. I think that's what that comes down to. And then let's look at the next one. All these things are things that you should be able to do without thinking in grade 11, and obviously then in grade 12. Here, simple application and recall of compound and double angle identities. So in other words, if you have to know off by heart the simple and compound formulas, because you have to be able to use them. So let's write it here. Okay, what are the simple and compound, your compound and double angle formulas? Well, first of all, we get, well, let's start with sine. Sine seems to be the one we always start with. So compound means inside my sine I've got two angles, an alpha and a beta, and they can either be added together or they can be subtracted. I'll still summarize it like this. So for sine, sine, I always say sine is same sign, different ratio. So in other words, sine is same sign. So if this is a plus, it will be a plus. Different ratio means the ratio is the trig ratio. So it would be sine alpha cos beta plus, and then this one just needs to swap, sine beta cos alpha. Okay, so sine is same sign. If this is a plus, that's a plus. Different ratio, so it's sine cos, sine cos. Okay, and then the angles swap around. These angles can't be the same. You can't keep them the same there. Okay, and so if it's minus, it would be sine alpha cos beta minus sine beta cos alpha. So that is for sine. For cos alpha plus beta, it's the opposite. It's different sign, same ratio. So it starts with cos alpha cos beta. So you see here the ratios are the same, but now the sign is different. If this is a positive, this one will be negative. And then it would be sine alpha sine beta. And then the same will go if this is a negative, then this will just be a positive because it's different signs and same ratios. Now for the double angles is super simple because if you know this one, then it's very easy to remember the double angles, because a double angle would be sine of, let's say, double angle. So let's say 2a, which means it's just a plus a, which means it's sine a cos a plus sine a cos a, and that's why this is 2 sine a cos a. Okay, this is an incredibly important a double angle formula to know, this one specifically. And then if we use our cos of 2a, so that would be alpha plus alpha would be cos alpha cos alpha. What is cos alpha cos alpha? That's cos squared alpha, and then it's plus alpha, so this is minus sine squared alpha, because this would be sine alpha sine alpha. So but these you have to know them off by heart. I promise you will not regret it. Practice to know them off by heart. That is maths also have things that you should know off by heart, and the formulas are definitely some of those. Not because you don't have a formula sheet, but because you need to recognize these formulas when they come up, and we will see some examples in the question paper. Okay, and then and that's it. The only thing that I can maybe add to this is that this one can obviously be written in a few different ways, because I have this formula as well, that sine squared alpha plus cos squared alpha is equal to 1. Okay, so I just want to write sine squared plus cos is equal to 1. So sine squared is 1 minus cos squared alpha. Okay, and that comes from our where did we write that? That is one of our standard what is it called? Fundamental identities. Okay, so that's one of our fundamental identities. So when it comes to the fundamental identities, this is one of those. So it's just rewriting it. Or I can say cos squared alpha is 1 minus sine squared alpha. These are just things that you should be so used to using them that they should just come naturally. And so if that's the case, I can replace this sine squared alpha. That sine squared alpha can be replaced with minus 1. So minus sine squared can be, and this can be replaced with 1 minus cos squared. So I'm minusing 1, and then so it's cos alpha minus 1, which is that minus 1, minus, and notice that minus cos. So that would be plus cos. So there would be 2 cos squared alpha minus 1. Or if I replace the cos square with 1 minus sine square, this time there's not a negative in front, so the signs all stay the same. So it's 1 minus sine squared minus sine squared. So it's 1 minus 2 sine squared a. So all of these are extremely important. And really, guys, I can't stress this enough. Know these formulas off by heart. Okay, and here you can see this is what we need to study. and know off by heart when we're studying maths. These three levels and this part here. Let's see in terms of level 2s, what ability should I be able to do? And I know this video is really getting long. I don't care. You can pause it and go on later. First, can you prove the fundamental trigonometric identities? Okay, can you prove the fundamental trigonometric identities? So if I go back there, so remember for grade 11, you should know the fundamental identities off by heart. The question now is, can you prove it? Okay, why is that true? Why is it true that sine squared theta plus cos squared theta is equal to 1? Okay, let me show them quickly. It's not difficult. It's just because sine squared is opposite over hypotenuse squared. Cos is adjacent over hypotenuse squared. So what you get is opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared, and then you get opposite squared plus adjacent squared over hypotenuse squared. And if you work in a right angle triangle with opposite and adjacent, when you square these two and you add them together, you are getting the Pythagoras. These two squared is equal to that one squared, and so that is the hypotenuse. Sorry. This is the hypotenuse. And so here at the top, you simply have hypotenuse squared over hypotenuse squared, which is 1. And that's why that is true. How about tan? How about tan? Okay, so tan is sine over cos. So sine theta over cos theta is equal to opposite over hypotenuse divided by adjacent over hypotenuse. One of my students taught me, when we divide fractions, you tip and times. Okay, so opposite over hypotenuse times hypotenuse over adjacent, which means, okay, those two will divide into each other so that I'm left with opposite over adjacent, and opposite over adjacent is tan theta. Okay, that's what we have there. So we need to be able to prove that. Use a sketch to find the value of trigonometric expressions, and this is very important. A very basic fundamental ability, and you will get one of these. I can assure you, you will get one. You did get one in your mid-year exams. So what is happening here? Okay. Whoa. Interesting, huh? So there's typically examples of this is, for example, if I took, well, let's say they give you some way in which one of the trig ratios, so let's say that they give you a trig ratio that can be simplified to some value a over b, whatever, and then they give you another trig ratio, and this time they say that trig ratio is bigger or equal to bigger or equal to 0, or smaller or equal. That's bigger or equal and smaller or equal to 0. So you know whether or not it is positive or negative. Now, they will always give you two pieces of information. One will be some trig ratio, so it will be a sine, cos, or tan, and that can then be simplified. And then another element where you know whether it's positive or negative. And the whole idea is that you use your cast diagram to first figure out in which segment does this, or in which quadrant does this triangle lie? And then once you know in which, so here you will have, okay, let's say sine is positive and cos is negative. Okay, where's sine positive? Here and there. Where is cos negative? Cos is negative here and here. So the two conditions are met in the second quadrant. So then you know to draw a triangle here in the second quadrant. Let's say you work out that, okay, the tan of theta is negative and sine of theta is negative. Those two conditions. Well, where's tan negative and sine negative? Tan is negative in these two quadrants, this one and that one. Where is sine negative? Sine is negative in this one. Then you know you're in the fourth quadrant. So the first thing you do when you have to use a sketch to determine to solve some other trig ratio, the first thing you need to do is find out in which quadrant must I draw my sketch. The second thing I must do is then draw the triangle. So let's say I know my triangle is in this quadrant. Then I draw a right angle triangle and always make my angle with the x-axis. It's either there or it's here. So it's either in the second quadrant, the third quadrant, or maybe even in the first quadrant if you're lucky. Okay, so it will look something like one of these four, not all of these four. Okay, so the next thing I need to do is I then use this A and B, because these will represent side lengths. They represent side lengths. And so if it was sine, then this is opposite over hypotenuse. And then I use, so first find the quadrant. Secondly, you draw the triangle. Thirdly, you find the sides. And remember, there must be three sides. So one of the sides is going to be solved with Pythagoras. So depends on what these do. If this is a sine, then the value there would be opposite and hypotenuse, and you can find the adjacent using Pythagoras. If this is tan, then this is opposite over adjacent, and you can find the hypotenuse using Pythagoras. But that just gives you all three sides. And then the fourth step would just be to solve the question. So they are going to give you this, and they're going to ask you a different trig ratio, and ask you, well, what will this answer be? And then you've used your sketch to go and calculate that. We'll look at an example in the next video. Okay, that is that's the second one we're going to look at. Okay, simplifying using a sketch to find the value of a trigonometric expression. So there's different examples of these. Okay, the next one is simplify standard trigonometric expressions using fundamental identities, co-ratios, and reduction formulas. That is just very typically, they give you, it's literally just applying your formulas. I say pas, cas, and das. So pas is positive, acute, and simple. Cas is cos and sine. And das is do algebraic simplification. Okay, pas, cas, and das. So it is an expression that where you would end up having to apply your these things using fundamental identities, using the co-ratios, the reduction formulas, and then using algebra and putting all of these things together to simplify an expression. And the only way to really show you is with an example. So and since this is not really about examples, but this just means you should be able to simplify trigonometric expressions. That's what it comes down to. Simplify trigonometric expressions and proving identities. So proving standard trigonometric identities using fundamental identities. So simplify and prove. These two basically is exactly the same technique. Change all your angles into positive, acute, and simple angles, and then use fundamental identities, which basically just comes down to replacing sine squared plus cos squared theta with 1, and replacing tans with cos. Sorry, tan with sine over cos, and then just simplifying with algebra. Finding the value for which an identity holds or does not hold. So here it simply comes down to an identity will almost always be some expression over another expression. So ignore that, over another expression, and this will then be equal to another expression over another expression. And so they'll always ask you for when would, or not always, they'd often ask you for what values will this identity work, and for what values will it not work. And it always comes down to this: it cannot work for any angles that makes the expression undefined. And so whenever one of the denominators, so all you do is you take the denominator and equal it to 0, or you can say is not equal to 0, whatever it is. And then you just solve it. So if it says that, well, sine theta must not be equal to 0, then this expression, if there's a sine theta at the bottom of this whole expression, whatever is at the bottom, it could be a whole big expression, or on this side it could be something like 2 sine 2 theta, something like that, is here at the bottom. Well, then you say, well, 2 sine 2 theta is not allowed to be equal to 0. Then this expression won't work. And so then you say, okay, well, that means that this thing can't be 0. This thing will be 0 if theta is 0. So theta is not allowed to be 0. Then this expression won't hold. It's not allowed to be 0 or every rotation around 0. So 360 times k. So theta can't be any 0 or multiple of 360. So rotation. So I'm just plus minusing a rotation, but I don't need to do the plus or and minus because k is an element of integers, so it can be positive or negative values. Okay, but something like that. So they just take the expression in the denominator and say it's not allowed to be 0. That's this one. Next, finding the general solution or the specific solution of trigonometric equations. Okay, and so what that means is if you're working in a trigonometric equation, then what you're doing is you're saying, color to be used. Okay, we're saying if you're solving a trigonometric equation, what you want in the end is trig theta is equal to a constant. This is what you're trying to get to. And it's not so easy to get to that. That's your aim, is to get to that. Another aim you could try and get to is trig theta equal to another trig theta, a different trig theta. And then there's ways in which you can solve this, and you can go and look into that. So for example, sine theta, not necessarily theta. It can be so you don't necessarily want trig theta, you want trig of something. I shouldn't have said theta. You want trig of something, and this is not going to work. It will make it white, but that's okay. Ghost. Trig of ghost, and so you want trig of ghost equal to trig of another ghost. So one trig equal to another trig. Okay, this could work, or having a trig equal to a constant. Any trig expression equal to a constant, that will also work. Okay, so and then once you're here, you get your reference angle. Always, it doesn't matter which way you go. From here, you get your reference angle. And from your reference angle, you say, okay, well, that means and now I have to do ghost, whatever is in the ghost, whatever is in here, it can be a whole expression, it doesn't matter, it can be something in here, is now equal to, and then usually just equal to your reference angle, or it's, again, the ghost, equal to something, like wherever else the angle is positive. So you get your reference angle by using arc trig. So trig minus 1c. Okay, that gives you reference angle, and then you just, here it depends on in which quadrant you are. You just look for where it's positive. If it was sine, then it would be 180 minus. If it was tan, it would be 180 cos. If it is just if it's cos, then it would be just here in the negative. So you can either say 360 degrees minus, or you can just say minus, because 360 is a rotation. You don't have to write it if it's there. Okay, so and then plus, and 360 degrees times k, plus your reference angle plus 360 degrees times k. If it is tan, then it's plus, then there's only one solution. If it is tan, you can just have your ghost, and you have your reference angle plus you don't need the minus because you're using k, plus 180 degrees times k, where k, and you always put this with, is an element of integers. Great. And then I'm not going to get to everything because I'm going to keep this video to an hour. So let's just finish. Prove sine, cosine, and area rules. Okay, you can go and study that for yourself. What is the sine, cosine, and area rules? Just to remind you what they are, the direct application of sine, cosine, and area rules. So if I go there, sine rule is that if I have any triangle, so this is now an exception where I'm not working in a right angle triangle anymore. Then sine A over A is then the opposite angle, is equal to cos A, sorry, it's not equal to cos A, I'm lying. It's equal to sine B over, so sine of that angle would be sine of that angle over the opposite side length would be equal to sine of that angle over its opposite side length. And that also would be equal to sine of this angle divided by its opposite side length. So that's the sine rule. Know the sine rule. Okay, important to know the sine rule. And the cosine rule, similar, but different. It works in this same setup where what you say is, okay, I have okay, when would you use the sine rule? You'd use the sine rule because you would need one of these two, and for example these two. And so what you'll see is you have an angle and an angle, a side and a side. So whenever you have three of these, so either two angles and an opposite side, and that's very important, you need an opposite side. So if I have two angles, those two angles, for example, and two angles, that's sides. If I have two angles, let's say I've got B and I've got A, and I've got either A or B's opposite side. So let me rather say this. You need at least one angle opposite side pair. And then it doesn't matter what else you have, either an angle or a side, it doesn't matter, you can use this. So you need at least one. So when would we use the sine rule? Is when you have an angle plus opposite side. Then you can use the sine rule. Now, if you don't have an angle and an opposite side, if you don't have an opposite side, it means you have the other two sides. And so if you have the other two sides, you need this inclusive angle here. Now, this is the cos rule. The cos rule says that if I have cos of B, angle B, is equal to, and then it takes these two side lengths, A squared plus C squared minus 2 AC. Notice these are all the values that I have. Cos. No, I am making a mistake. I do apologize. That's not what this one is. It doesn't say. Okay, let's do. Okay, there we go. I've got C, that's not working. I've got C squared. You can't see that C very nicely. I'll make it thicker. C squared, in other words, not C squared, the angle that I don't have, the side that I don't have, B squared. B squared. Let's make it darker. Okay, B squared is equal to these other two side lengths squared. Notice it's like it looks like Pythagoras. It looks like Pythagoras, but it's not Pythagoras because we're not in a 90-degree triangle. It subtracts a component. It subtracts 2AC, these two multiplied, cos, and then the angle that I have, cos B. And so obviously notice what I have. I have I either have three sides, and when I have three sides, I can use it to calculate one of the inclusive sides. So if I have all three sides, I can choose any one to be the inclusive angle, as long as this side length is the one that's opposite the angle that I want to calculate. So I either have three sides, or I have two sides. I have two sides and their inclusive angle. So A and C, and then the angle that they make. And then that can be used to calculate B using cos. And so this is the application of these two, sine and cos rule. And then obviously the area rule, which and I've run out of space and definitely out of time. But so for the area rule, I say, okay, so the area of a triangle is equal to half AB sine C. So it's here's C. So I take side length AB that makes up the angle. So it's whatever sides I take times sine of the angle between them, the angle that they make. Half of that gives me the area of that triangle. Okay, great. And as you can see, this was an hour video to take you roughly through Well, we still have all of this to do, proving compound and double angle identities, using a sketch to find the value of trigonometric expressions. You'll see there, okay, still in grade 12, simplifying standard trigonometric expressions, proving standard trigonometric expressions. The only thing that comes that gets added now to these is that we need to use double and compound angle identities as well. So in grade 11 we didn't need to use that. We only learned them in grade 12, but then we do exactly the same thing, finding the equation of a circle, finding the general solution of a trigonometric equation, and then direct applications of sine and cosine and area rules. So as you can see, it's basically the same. So far we have looked at then doing this, and then level 3 is literally just compounding these things together by as you can see, there's quite a bit of extra there, and you can go and work through that. I wanted in these videos just to focus on the basics of what you should be able to do, and if you practice these, guys, you'll be fine. So I'll make another video in which I actually then just do the questions in the test, because you'll see that just by doing what I just did, just by doing what we just did, I didn't do graphs. The graphs are under the trig and the functions and graphs in here. So I didn't do graphs in here, but yeah, graphs can be yeah, I suppose I should just do another video with the graphs in. And yeah, but other than that, graphs, I can do all of these questions just by the basics that I've just showed you. All of these questions, it's just not the graph question, and that's level 1 and 2 things that I showed you, and you can actually now just apply them and do them. Okay, excellent. So I'll see you in that video.